So I've got a tubular linear motor, and it's a Nippon pulse motor, and we're going to take a look at how to configure it. It's a sine cosine 1 volt peak to peak, and we're going to configure it with an ACJ REV01 arm, which can take sine cosine in on the incremental A naught, B naught. I've got the specifications for the motor, so they provide it on the web page. I'm just running it on 24 volts. It's got low resistance, so we can deliver like the 1 or 2 amps of current required even on 24 or less voltage. Apparently you can have a lower voltage. So we'll take a look at the video here and see on the camera. This is a payload of 60 grams. There's the coils inside of the tubular linear motor. There's feedback sensors in here that are analog sine and cosine Halls, so 2 Hall sensors. The rod has magnets, a pair of magnets, a north and a south is 24 millimeters. You could have a longer stroke with more pairs of magnets, so I think this stroke is a bit over 24 millimeters, so maybe it's got another set of pairs of magnets. If it was 1 pair of magnets, it would be absolute within 1 pair of magnets, but you have to do some homing otherwise. So what I've got it doing now is it's going to move up to the negative limit to the hard stop and back down. Then it makes a fast move down up, back to center. And I disable halfway through. You can see we go to blinky light, and there's a counterbalance which keeps it from crashing. So the counterbalance is not a spring. It's this magnetic linear counterbalance. So unlike a spring that you push on and you change the force, this has a constant force over the range. It's like a compensates for gravity. Normally we do that in the drive by setting the continuous current, but if you disable the drive, you're going to crash. Let's take a quick peek at the wiring. I got the ACJ here. The motor wires are white, black, red, UVW. I've got 24 volts hooked up here from a little supply that can hardly do an amp, but it seems to be running okay. And I've got sine plus on A, sine minus on B, which is blue and white, cosine plus on B and B naught, which is yellow and orange, and then I got +5 and ground, red and black, so that's hooked up to the feedback connector here. I got power coming in and motor going out. I got a serial adapter, SER USB-S for Samtech connected in here, and if I had a CAN, I could do a CAN USB-01 plus an ACJ network kit. That would do the CAN, but I've just got it running a CVM program standalone. So here's the stage and the drive, and then in the background you can see the Nano, and this Nano Plus will have sine cosine as soon as it's released. Maybe I get a beta unit, but so what is this device that counters gravity? It's some kind of anti-gravity device. I'm not exactly sure of the details. I'm still waiting, but I did find this Back to the Future car that seems to exhibit a similar kind of anti-gravity behavior. So it kind of floats, but in a linear way, unlike a spring that you push on it harder, you get more force. So it's not a spring counterweight. Again, for the setup, we would configure the basic setup as a brushless linear motor, low frequency analog as the commutation, as the interpolation for position off of the sine and cosine, and analog commutation. pair of magnet distance here is 24 millimeters, and you can enter practically any value here. This is just resolution, so it's 1 micron of resolution. The accuracy really depends on the placement of the magnets and the Hall sensors and how accurate, the signal to noise, good cabling, grounding, shielding. I should talk some more. If you had a brake, you could set a brake stop time. You can come to a controlled stop when your hardware disabled. I'd recommend that. So give yourself 100 milliseconds to stop, and at a slow speed, and a little bit of settling time, and that's a good value for coming to a controlled stop and then let go. On this drive, I've hooked up the dynamic brake to short the motor wires in case I'm moving at full speed when I disable. So this precaution would be a better controlled manner for stopping. Just a can, and then we'll take a quick peek at the CVM control program and the scope here. In this program, I waited for 1 second, power up or reset. I set this parameter 6F to 8, that's bit 3 for the dynamic brake. I do a homing, I do a fast move down, fast move up, I move to center, I disable so I can show that you can not drop, wait for a time delay, and then I just jump back to repeating this whole thing again. Very simple CVM program, and on the setup tab I chose registers to select a sequence, R0, and R0 is always 0, and there's a checkbox for run on power up or reset. So on power up or reset it'll start running and it waits for a second, so on and so forth. Makes a good demo, so just plug it in and the demo will run. We can see during the recording of the sine and cosine that we got the voltage sine and the voltage cosine. So while we're moving through the profile, accelerate, run, decelerate, and stop, you get a little bit of following error, then it settles, and you can see the voltage sine and cosine is 1 volt peak to peak. It's about plus or minus 500 millivolts on the sine and the cosine, and then I'm tracing the actual current. So for this move, it's consuming about an amp, and I can repeat this over and over. This is about 0.5 amps RMS, which is actually 0.707 amps continuous. So the motor data goes in here, inertia, peak and continuous force, theoretical speed, 3 volts per kRPM, about the same for Newton meters per amp, but this calculated out to be the amps peak versus the amps RMS. I calculated the initial tuning values, but I did some tuning, got a little bit more current loop bandwidth, about 1 kilohertz, and you can test it there, set the peak and continuous current. The motor's rated for 0.5 amps RMS, so 0.707 amps continuous. And then the tuning of the velocity loop, I had to crank it up again, but turn down the integral. If it was a longer stroke, I'm sure we could hit this speed, or if it wasn't vertical with a constant force, it might go a little faster, but that's a velocity limit. And then I tune the position loop. Seems like there's some load on here, so turn the PP down, little tracking window, and I turn the feed forward off so I can have some error while I'm moving and hopefully settle a little better, unless it's some kind of scanning application. A little bit less VFF is nice, allows some error and settles nicely. For the filter, I chose a single pole 100 Hertz. Never have more bandwidth than you need. It looks like I got about a 10 or 20 Hertz position loop, so perhaps 100 Hertz of velocity is fine. Maybe about 1 kilohertz, actually 800 Hertz of current loop bandwidth. Unless there was no load or very light load, then you could push the poles out and crank up the gains a little bit, but still no oscillation in the velocity loop. For the ACJ specification, I used the REV01 data sheet, and I'm just checking here. ACJ, we're still making the old one, so no more -S option, no more -R option. If you have a resolver, then it's the CSR resolver adapter with the ACJ REV01. No more -S option. You get the ACJ REV01 and take sine cosine in on A and A naught, B and B naught. But there's a good description of wiring the feedback device here. So there. So sine and cosine go in. There's a shield on pin 1 or pin 14. So the shield goes. Don't connect the shield to the motor case. Connect it to the drive case, which goes to earth. And then +5 and ground come out. You don't need Halls because it's got analog Halls in on the sine and cosine encoder, which we do for commutation and interpolation. And again, I'm running a 1 micron resolution here. That's not accuracy. You don't need Halls when you have analog Halls. And so that's the basic wiring diagram. And of course, the motor UVW. I never use a fuse on the motor wires unless it's like a $10,000 motor, and then maybe if I mess up. But there's current limits here, I²T, so you're good. And the power supply, earth at the drive. You see how the return line of HV is also finding a path to earth. And earth to pin 1, protective earth or frame ground, so that the case goes to earth, so that when your shield connects to it, it finds a path to earth. Power supply, 24 volts, local cap. There's a bulk capacitor inside the drive. There's not a lot of regen here, so I don't think we need very much capacitance. Everything seems to be fine with no regen. Okay, thanks for watching.